Good day, everyone. My name is Pramod Khargonekar, and I'm recording this presentation from my home in Irvine, California. Let me begin by saying how pleased I am to be part of this workshop at ECCV. And I want to start by thanking Sachin Talati, who is a friend and a collaborator from many years, for inviting me to this workshop. I'm just delighted to be here and share some thoughts with you. My talk is entitled Kalman Filtering, Sensor Fusion, and Eye Tracking. It's in 4 parts. I begin with an introduction to Kalman filtering, then multi-sensor, multi-rate fusion. Then I'll talk about distributed, decentralized Kalman filtering, and close with some thoughts on potential for eye tracking. At this point, it's good for me to tell you that I really know very little about eye tracking. I think the reason Sachin invited me was because of my connections to Kalman and Kalman filtering. And that's a great place to begin. Kalman is probably one of the most famous scientists, certainly from control theory world, of last many decades. He's the founder of the field, and I was very lucky to be his graduate student, one of his last graduate students. He passed away in 2016, just about 4 years ago. And there is a plethora of articles on him, and I've highlighted some of them here. An obituary that appeared in Control Systems magazine, and a tribute to him by several of his students. And then I wrote 2 essays on him, a personal tribute to him, as well as some of my reflections on the way he thought. So let's jump in. What's Kalman filtering? Now, if you know Kalman filtering, this is too elementary for you. But if you don't know, this will be a very quick introduction, and it's sufficient for me to talk about the rest of my ideas. So Kalman filtering, we start with a system model, essentially a linear system and Gaussian noise. So the system is given by a difference equation, x at time k plus 1, t is the sampling period, is a linear function of the previous state at the previous instant, akxt, plus an input term, bkut, and a noise term, w. Along with the state equation, you have measurement equation given by the second equation, namely y equals cx plus du plus v. V is the measurement noise. And then for the noise, we make assumptions that it's Gaussian and zero mean. And we characterize that then using its covariance. So covariance of the initial state x0 is given by p0. Covariance of the system noise is given by Q, and covariance of the measurement noise is given by R. Everything is a function of K, function of time. It doesn't have to be. You can do the simpler case of linear time invariant, but it really makes very little difference. So we just stay with this more general version. So it's a linear time varying discrete time system. Sampling period is T, state variable is X, input is U. This is supposed to be known. And so essentially, you can take this out of all the equations. And for simplicity of this talk, I'm just going to make it equal to 0. But it creates no big deal. Process noise W, measurement noise V. With that setup, the Kalman filter equations are very, very simple and straightforward. And they come in 2 parts. One is, what do you do with the estimate of the state? And then what do you do with all these covariances, okay? So the estimate of the state is propagated in time in 2 steps at each instant of time, or each sampling period. One is what is called the time update. That's the first equation. So suppose you had an estimate of the state at time kt using all the information that was available to you up to that time instant. So that's what the notation x hat of kt given k means. You knew everything up to time k. What's your best estimate of x at time kt? Denoted by x hat of kt. From there, to calculate your best estimate of time of the state at time k plus 1t, that is the next time instant, all you do is propagate that estimate through the state matrix A of k. So you multiply A of k times the prior state estimate. That gives you the estimate of the state at time k plus 1t. Now, what about this estimate x hat at time kt, given all the information up to time k? That's also very simple. What the Kalman filter says is, that equals its estimate given information up to time k minus 1. So that's the first term in the second equation. And then you add to it a term that depends on the difference between the measurement y at kt minus your estimate of y given your best estimate of x hat given information up to k minus 1. So you knew up to k minus 1. At time kt, you get new measurement y of kt. You subtract from y c times the best estimate of your state up to information k minus 1. You look at that difference, that's called innovation. That's the new information in your measurement y. You multiply it by a matrix L, that's called the Kalman gain, and you add that to your estimate of the state at time kt given information up to k minus 1. The second equation is called the measurement update, and you can see why. Because what it is doing is telling you, you had information up to time k minus 1. You had an estimate. You get new information at time kt. What do you do with it? You subtract from it your best estimate of y, that's c times x hat, multiply by L, add it up. That gives you x hat at kt time, given k. Now, if you combine the two equations together, now you can see it gives you a recursion of going from best estimate at time kt given k minus 1 to best estimate time k plus 1t given k. And you can just propagate this further. So two steps, a measurement update and a time update, and you just keep recursing. Now, what about this gain L? Okay, that's the new thing here. This L is calculated using propagation of the covariances. So the first equation in the second half of the slide tells you how do you propagate the covariance of the state error at time k given all information up to time k. So P inverse of k given k is basically a notation for the covariance of the error in estimation. And that propagates as P inverse of k given k minus 1. So what you knew up to k minus 1. And then you add to it a term corresponding to C times R inverse. Now what is R? Remember, R is the covariance of the measurement noise. So what it tells you is your error in state estimation increases by something that relates to the measurement noise, which makes sense because you are adding something based on y in estimating x hat. Well, since y is noisy, it is potentially going to increase error. And this formula tells you exactly what the error in what the covariance increase is going to be. You calculate L using that formula, and then you propagate this covariance P to the next time step using the state equation. So that's the last one, A times Pk given K, A transpose plus the measure, process covariance. Very beautiful, simple set of equations, recursive, and tells you the best estimate. And what Kalman proved is that this is optimal, assuming linear dynamics and Gaussian noise. He did this in the late 50s, and it's probably, with no exaggeration, the most important and impactful result from control theory over the last many decades. That's why he's the father of the field. And I would argue that it's one of the most important results to arise from engineering, particularly engineering theory or mathematical engineering. It's equivalent to Bayes' theorem. So under linear and Gaussian assumption, what these previous computations do is essentially apply Bayes' theorem. There are myriad extensions of this to continuous time, nonlinear, non-Gaussian, distributed, networked, and I'll touch on a few of these things. Algorithm is real time, it's online, it's recursive. So it's really, really suited for implementation to a wide variety of systems. You saw all these matrix inverses and so forth. The enormous amount of work has been done, how to compute those efficiently. What do you do with these inverses? This P and Q, P is supposed to be positive definite. How do you ensure that? So there are things like square root algorithms that ensure positivity and make inversion easy. I cannot tell you how much work is there in all different aspects of theory and implementation of Kalman filtering. And as a result, there are applications in just a wide variety of fields in engineering, in sciences, physical sciences to behavioral sciences, all fields of engineering, and it shows up in many of the technological products. And I have to add for this audience, applications in machine vision. And there is just voluminous literature around Kalman filtering. So there's a very rich heritage he has left behind for us that we can leverage. Let me now turn to multi-sensor data fusion. So the idea here, and this is again another field that's quite old, and I'll explain that in the rest of my talk. The idea here is, can we combine data from multiple disparate sensors to arrive at a unified estimate of the unknown system or unknown signal? So it really is a very kind of a concept, a general concept, and the main focus is you're looking at something with multiple different modalities of sensing. So electromagnetic, could be acoustic, any kind of imaging. You can just think of all different kind of sensing, but they are sensing the same system or same signal or same environment. How do you combine all those sensors to give you a unified best picture of what's going on? Because it's a fairly general idea, there is a wide variety of techniques to address disparate challenges related to system, to the sensors, and the data characteristics, because the data can have different kinds of granularity, accuracy, so on and so forth. And these techniques, you can sort of think of them as probabilistic. Dempster-Schaeffer theory has been proposed for multi-sensor data fusion. Fuzzy sets, random sets, all sorts of techniques have been proposed depending on the nature of the system and nature of the data and the nature of the sensors. And there are many application domains. I think a lot of impetus for sensor fusion came from the defense applications. So aerospace or naval applications, think of ships sensing their environment. I mean, you can just, you can let your imagination run and you can see where this sort of an idea would have application. In current day reality, sensor networks, IoT is creating a huge opportunity for multi-sensor data fusion. Things like digital twins, manufacturing, monitoring of systems. Again, you can see why the idea of multi-sensor data fusion would be very important. Robotics is another field, biomedical. Applications where you say imaging, for example, your multimodal imaging, how do you combine information from different types of sensing in biomedical applications. And then finally, I certainly want to say physical sciences. So you think remote sensing, weather prediction, there is a whole field called data assimilation. That's nothing but data fusion. So it's a very, very powerful idea. And again, as I said, it's a topic that's been around for quite some time, and there are some nice review papers. It turns out that Kalman filtering has a big role to play. And so here I'm just quoting from a review paper on multi-sensor data fusion, where the authors state, nonetheless, the Kalman filter is one of the most popular fusion methods, mainly due to its simplicity, ease of implementation, and optimality in a mean squared error sense. It is a very well-established data fusion method whose properties are deeply studied and examined both theoretically and in practical applications. And then he goes on to talk about weaknesses. On the other hand, similar to other least squares estimators, Kalman filter is very sensitive to data corrupted by outliers, etc., etc. The main point is Kalman filter plays a very significant role in multi-sensor data fusion. And I explained to you the linear Gaussian version of the Kalman filter. There are many, many extensions that are relevant to, particularly to sensor data fusion. EKF, extended Kalman filter, is probably the simplest extension that applies to nonlinear system. And the idea here is you still characterize your state estimate and noise as Gaussian random variables. You still describe state error as a Gaussian random variable. You propagate the state estimate through the nonlinear system, and you calculate the output equation using the true nonlinear system. But all the covariances and so on and so forth, you propagate them through the linearization of the nonlinear system. Okay, so it's probably the simplest way to extend the theory to nonlinear systems. Then there is a version of this called uncentered Kalman filter, which is a little more complicated than EKF, but it tends to be much more accurate. It still uses Gaussian random variables to describe the state estimate and state estimate error and noise. But what it does is it takes a few selected points. So in EKF, you only look at the mean and covariance, and you just propagate the mean through the nonlinear system. Here, you actually look at a few points on the distribution, and they're very carefully chosen using something called the uncentered transformation. And you use those few points, you propagate them through the nonlinearity, you calculate the covariances and propagate the system that way. And that is, gives you much more accurate estimates compared to EKF. Then there is the whole body of literature on particle filters or Monte Carlo algorithms, which are, you can think of this like much more computation intensive versions of UKF, where you just select a whole bunch of points and propagate the entire distribution and calculate the properties of the distribution. I mean, a general result in nonlinear filtering is the best estimate is a conditional mean, except your distributions are no longer Gaussian, so you cannot characterize them simply. So particle filters kind of get over that, but they tend to be much more computationally expensive. And there are other related methods to Kalman filtering. One particular version that I think is potentially of interest for eye tracking and other applications is what is called multi-rate Kalman filtering. So here you imagine you have a bunch of sensors, except they are sensing at different sampling rates. That may be because of their bandwidth constraints or their physical characteristics. So you imagine a sensor 1 operating at sampling time n times t, and sensor 2 operating at sampling time m times t, where t is a common period. And n and m are two different integers. And you can imagine n different such sensors, each operating at a different time, different sampling rate. What do you do? Well, I mean, in principle, the Kalman filter equations generalize quite easily to this case, but the notation can get quite hairy. One generic approach to multi-rate filtering is what is called lifting. So let's start with, suppose you have a discrete time sequence Z0, Z1, Zn, etc. You pick an n and you stack these vectors. So here as n such samples, so 0 up to Zn minus 1 becomes a super vector Zn at time 0, and then Zn at 1 becomes the next n samples, and so on and so forth. And if you do that, you can convert using this is called lift. So you lift the sequence to this higher dimensional space, and you can just sort of rewrite all the equations, and a multi-rate system can then be rewritten as a standard discrete time system of the kind I started with, using this lifting idea. And then you can try and calculate all the variables you are interested in. There are many papers in control systems literature based on this lifting approach. This is just one of many. And the nice review paper that I have shown here, where there is an overview of multi-rate, multi-sensor systems. And here, as an example, they use something called the data block technique, which is not that dissimilar from the lifting technique, where you take blocks of data and process them and propagate your estimates. Moving on from multi-rate Kalman filtering, I want to talk about this distributed or decentralized Kalman filtering. So what if these sensors are distributed on a network, perhaps? They are not all on the same physical location. What do you do then? Well, there is, again, quite a bit of history on this question. Some of the oldest papers go back to 1970s. I've shown some. Kalman filter algorithms or multi-sensor systems in 1976 IEEE CDC. And then another paper in the Transactions of Automatic Control in 1988 that had some of the earliest results on this. And you can see the different kind of architectures for the distributed or decentralized case. Where do the signals come? Where do they go? Where they are processed? And there are, there's a lot of choice to be made here. And then there is application of this distributed filtering to sensor fusion, which is the topic that, that we've been focusing on in sensor networks. There's a very nice paper by Olfati Saber that I mentioned here that is definitely worth a read. And let me just now explain the key ideas behind this. So suppose you have J different sensors described by the output equations. Is the same process dynamics, except that you got J different outputs. Well, you know, conceptually, this is not what you would actually do. Conceptually, what you could do is combine all the outputs into a single vector Y and apply Kalman filter. Okay, I mean, you can do this, and that would be your optimal estimate if you didn't have any constraints on the network or distributed sensing. What is done in this body of literature is you create local Kalman filter and fuse the results. So one sort of way of thinking about this is you create a Kalman filter at each sensor, generate state estimates and covariance matrices, and then combine these estimates. So there is a whole variety of algorithms for exchanging information between sensors with or without a central processor. So there are techniques where there is no central location. They're just talking to each other. That's all, peer-to-peer, as well as where you can combine results at a central computer. And there are analytical results on performance of the resulting estimates, convergence of the estimator, etc. And again, there is a huge body of literature. I've shown you a few already. So here is an example of the kind of algorithms that come about. And this is the old Hashemipour paper from the transactions. And what it shows is how you combine both the estimate of the state as well as the covariances at different locations. So the first equation shows you calculate covariances, error covariances of the kind that we discussed for the Kalman filter at different sensor locations. And how do you put them together and propagate an estimate of the covariance? And then how do you propagate state estimates? So this second equation shows how you propagate the best state estimate from the local state estimates driving. So here you don't have to combine all the measurements. You simply propagate the covariances and then compute the state estimate. This is just one example of the kind of fusion that can be done, but there are many other examples. So Olfati Saber's paper that is more recent and talks about there being a sensor network. What you do is that each sensor node, you have two things, a covariance filter and a consensus filter. And you create what is called a micro Kalman filter that gives you a state estimate at that node. And then these nodes talk to each other according to the diagram shown to the right, where they exchange information with each other described by the network connectivity. So which sensor can talk to who? And what Olfati Saber shows is how these types of algorithms can converge, assuming, you know, assumptions would be like network is connected and things of that nature. Leads to results on the quality of the estimate and its convergence. Okay, now to my final part of the talk, which is what's the application to the kind of questions that are of interest to this workshop. So let me first begin by, again, repeat by saying that I really don't know a whole lot about eye tracking, but in preparation for this workshop, I did study the literature and then came across this wonderful paper by Greg Welch, who I suspect most of you know, on the history on the use of Kalman filter for human motion tracking in virtual reality. And in the paper, he says that one of the earliest published accounts, although this is not the earliest actual use because this was published in '88, is Rebo's master's thesis. And then so he goes over the entire history of the use of Kalman filtering. And then I just thought this quote from his conclusion section is particularly interesting. Information and associated databases will be organized by physical location and time, allowing users to both store and retrieve past, present, and future information in the context of physical locality and direction of gaze. The Kalman filter will undoubtedly play a role in this vision, no matter what the underlying source of signals. So I was really pleased to see that in this review paper, when it comes to conclusions, he says that Kalman filter, he expects Kalman filter to play a significant role. Now, putting this a little bit more current context, I mean, one of the both merits and difficulties with control theory world is it's very heavily based on dynamical math models. So all of control theory is sort of predicated on having mathematical models of the system that you are trying to either predict or control or what have you. And certainly Kalman filtering and quality. I mean, if your models are good, it can do an amazing job. If the models are not so good, then there is a problem. Now, the newer machine learning methods like, you know, deep learning and all those types of techniques avoid model building, and they simply rely on data and a generic neural network, for example, and some training algorithms or learning algorithms to solve similar problems. And so one of the things that I think is of great interest is, can we combine the strengths of model-based approaches with these data-driven learning type of approaches. And you know, there are some recent examples that show that there is probably merit to this idea. So this is a 2016 paper from Symposium on Mixed and Augmented Reality, Learning to Fuse. Again, I don't know these authors, but I imagine some of you do. And I thought this paper was very interesting, and it came up with what, you know, it's really one of the really interesting ways of combining model-based and model-free approaches. So you have, and their problem is to combine two types of sensing. So it's sensor fusion, inertial sensor, camera sensor, and then you use an LSTM as well as the visual tracker, and you apply the Kalman filter to the output of an error detection system. And that calculates a final pose, and that is then fed back into the trained LSTM. And then the results show, you know, significant improvement in the performance of the resulting system. So the main idea for their work was, can combining these two sensing modalities using a mix of Kalman filtering and LSTM, and so you can see on this chart in the results a major improvement in, for example, the failed frames and overlap, both of these metrics. Eye tracking, again, there are many different issues in eye tracking. So there are issues involving eye movements. So there are different kinds of eye movements, fixation, saccades, and then smooth pursuits, especially following dynamic stimuli, like say in video. Pupil detection is a big part in eye tracking. And then the issues related to calibration, tracker calibration, slippage or calibration drift. Now it turns out that for the movement problem, there is actually a rich body of literature where Kalman filter has played a big role. And I think probably one of the most pioneering papers in this goes back to Sauter et al. In 1991. This was for remote eye tracking, not the kind that you would use in virtual reality, but again, they applied Kalman filter for eye tracking movements. And then there is the really thesis of, high impact thesis of Grindinger on eye movement using Kalman filter, and then a much more recent paper by Komogortsev and Javed Khan on Kalman filtering for eye gaze guided computer interfaces, where they make, in fact, in that paper, they make math models and apply Kalman filter for their eye gaze problem. There have been publications in the control theory literature on this. So this is actually a 2002 paper, a non-intrusive Kalman filter based tracker for pursuit eye movement. So that's a dynamic pursuit eye movement. And I thought I would just show you a result from their work. This is in American Control Conference, so not the kind of conference that your group might go to. And again, that shows on the right-hand side, the result from an application of a Kalman filter against the true eye position. And on the left-hand side is a test sequence that simulates. So you can see that it does a very good job of reducing error and smoothing the estimate. My final point is I believe that control theory has the potential to provide useful tools. And here I picked a very recent paper by one of the leading groups in eye tracking. It's called Get a Grip. It was at the last year's ETRA. And there is a quote, and this is the paper that makes the case that the major remaining challenge in eye tracking for virtual reality, augmented reality is device slippage, which leads to calibration errors. And so this is kind of a sensor drift type of problem. Again, I don't know all the details of this, but the question of sensor drift and can you automatically have sensor drift, it has some old history. And in fact, this is where I thought I would just show one of my own papers where I worked on a similar problem, but again, a very different context. It was for semiconductor manufacturing. And we came up with a technique which could deal with sensor drift in real time as the process was happening, and it can self-correct. So it isn't complete self-calibration, because I think that's the way one could go to avoid some of this calibration and slippage problem is, can you have a completely self-calibrating system? This is a step in that direction. And the idea was relatively simple. We modeled the sensor drift via a state variable. And so it became a nonlinear Kalman filtering problem to which we came up with a solution and actually proved properties of its error characteristics and so forth. And so this is just an example. Again, I don't know how applicable it is going to be, but there is this whole body of literature in control world that I think has the potential to be useful for eye tracking. So to conclude, there is a rich body of literature on Kalman filtering and myriad extensions. There is a rich body of literature on multi-rate, multi-sensor fusion. I think combining machine learning techniques and some of these techniques from Kalman filtering world, I think has potential, as shown you one example of that. And then there is potential for solving current contemporary problems in eye tracking by leveraging this body of knowledge. So with that, I thank you very much.